Dear student, in the last class we have to discuss about the disjoint cycle, and we have to show that in the end if we have a two disjoint cycles permutation, then they are commute. If we in the example last we have to show that if they two are not disjoint, then they are not commute. Now we start today's lecture with the important theorem of product of disjoint cycles. So product of a disjoint cycles is we can say that every permutation pi of this Sn is either a cycle or a product of a disjoint cycle. So we can say that simply say that every permutation of Sn is either a cycle or a product of a disjoint cycle. So this means every permutation can be written as a either in the cyclic form or the product of a disjoint cycle. So the proof needs to be by induction on the order m of a points moved by pi. So if case m is equal to we have a 0, though pi is the identity permutation, then trivially one cycle. So if we have a m is equal to 0, then pi is a identity permutation, then we have a clearly this is a which is trivially is a m cycle. Now by the inductive steps, assume that m greater than 0 and I1 be the point moved by pi, and define the sequence by this: I2 is equal to pi of I1, I3 is equal to pi of I2, and so on. We have to going to the pi of I of r plus 1 is the same as a pi of IR, where r is the smallest positive integer such that I of r plus 1 belongs to I1, I2 up to IR. We just since there are only n points, the sequence must eventually repeat a value by a pigeonhole principles. We have to. So we claim that pi of I of r is equal to I1, and then suppose for contradiction we have to pi of IR is equal to some I of j for some j is strictly greater than or equal to 2. Then if pi of I of j minus 1 is equal to I of j, because I is the inductive injective being a permutation, it follows that j of I of j minus 1 is equal to I of r, and this means this contradicting the minimality of a r. So this contradicting the minimality of a r clearly. So now therefore pi of IR is equal to I1, and we have formed a cycle theta in the form of I1, I2 up to IR. And now if r is equal to n, then pi is a cycle theta, and if r is less than n, let p be the set of the remaining n minus r points not in theta. So then pi fixed every point in p means pi of p is equal to p, and theta is also fixed all points in p. So we have to fixing this pi is also, and theta is also fixing the points in p. Now the restriction of theta to I1 up to IR equals the restriction of a pi to the same set. This means theta restricted to I1 up to IR, then pi is also we have to restrict it to the same I1, I2, IR. So if we have restricting these two, we can clearly define a permutation alpha at a p is equal to same as a pi of a p. This means alpha of ij is equal to ij for j lies between 1 to r, and in other words alpha agrees with the pi on p and fix all points in I1, I2 up to IR. So that means this theta and alpha are disjoint permutation, and it is disjoint permutation means pi can be written as a theta into alpha. So theta and alpha are disjoint, so this means pi can be written as a theta into some alpha times. Since alpha moves fewer points than pi, by the inductive hypothesis alpha can be expressed as a product of a disjoint cycle. Therefore, pi can also be written as a product of a disjoint cycle, and this completes the proof of this theorem. So, we have to just say that any permutations can be written as a either as a cycle or as a disjoint cycle of a permutation. We take suppose we have a any 1, 2, 3, 4, 5, 6, and then we have to take a 3, 2, 1, 4, 6, and we have a 5 like this. So, if we write this in the form of this is equal to 1 goes to 3, 1 goes to 3, and then we have a 1 3, and then we have a 2 4 5 and 6, they are all single. So, this is all are the clearly this is the disjoint cycle, and if we write a 1 2 3 4 5, then we have to write a 2 3 5 2 5 1, and then we have a 4. So, 1 goes to 2, 2 goes to 3, 3 goes to you have a 5, 5 goes to 4, 4 goes to 1. So, we have a 1, 2, 3, 5, 4 is a complete cycle. So, any permutation can be either written in a cycle form or as a product of a disjoint cycle. This theorem is saying that you have any permutation either can be written as a cycle or is the disjoint cycle. So, now we have to move to the next theorem, and next theorem is clearly say that if we have a pi 1, pi 2, pi k are disjoint cycles in Sn, then the order of a pi is equal to pi 1, pi 2, pi k is the least common multiple of the lengths of the pi 1 pi I, that is if pi I is equal to n I I running 1 to k, then order of a this is nothing but is equal to we have a LCM of the n1, n2, nk. So, length of a pi I, length of a pi I we have to calculating. If the length of a pi 1, pi 2, pi k we call is a disjoint cycles, then calculate the length of a pi 1, pi 2 and pi k, and we take LCM of these lengths, and then we have to take a whatever LCM coming, that is called is the order of a that pi is simple is this. So, now we have to going to prove first this theorem, and then we have to discuss one or two problems. We can just write. So, let pi is equal to pi 1, pi 2 up to pi k, where pi I are disjoint cycles of a length Li respectively. So, L is equal to the LCM of L1, L2, Lk. Let LCM of a L1. So, pi 1 length of a pi 1 is equal to 1, length of a pi 2 is equal to 2, and length of pi k is equal to we have a k. So, we take a LCM of these two, L1, L2, Lk, we denote it as a this L form. So, since disjoint cycles commutes, we already show that the if cycles are disjoint, that means they are commute. So, there is some pi bar, pi 1, pi 2, pi bar is equal to this pi 1, pi 2 up to pi k bar, and then we have to just say that since given that L is equal to length of Li into Mi, some positive integer Mi, we have a L pi I to the prime is equal to pi I to the power Li and Mi, and pi Li to the power m, Li to the power 1 is equal to you have a 1 to the power m is equal to again 1. So, since Li is a order of m, so so this is order of a pi of I. So, this means pi to the power L is equal to we getting the identity. So, in this case we can share identity that this is equal to order of this is equal to L. So, similarly we just take into this pi prime is equal to L1 prime, L2 pi L is equal to L1 L, L2 L and so on, and this is equal to 1, this is equal to 1, this is equal to 1, so this all is equal to we can just say that into the 1. So, say suppose m is the element of a positive integer, pi to the power m is equal to identity. So, 1 is equal to pi to the power m, and pi to the power m is pi 1 pi to the power m. Similarly, pi 1 to the power n, pi to the power n, pi to the power k to the power m, we not need to show that this implies that pi I to the power m is equal to 1 for each I. So, we have to assume for contradiction that pi j to the power m is not equal to 1 for some j. We have to write for some j pi to the power jm is not equal to 1. So, then there exists some x 1 to n such that pi x to the power pi j to the power m x j is not equal to x. Since pi j is a cycle, so we have to pi j x is not equal to pi j x not equal to x. Otherwise, pi j m x is equal to pi j m minus 1 pi j x, and then pi j m minus 1 pi j x is equal to x. We have a m minus n, and the pi j x is equal to x, which contradicts this pi j to the power m x is equal to not equal to x. So, we have to just going into the similar fashion, and this can be write in the pi j to the power m minus 2 pi j to the power pi j x again x. So, we have to into this form we have to just get. So, pi j to the power m is equal to, we have to this is which contradict pi to the power j m j x is not equal to x. So, since pi I are disjoint cycle, for I is different from j, so pi I is equal to x. Thus, we can say that pi to the power m x is equal to pi 1 to the power m pi all to the power m, then this is equal to pi j to the power m x, and that clearly this is not equal to x, which contradicts pi to the power m is equal to 1. Therefore, pi to the power j to the power m is equal to 1 for all I. So, since pi I to the power m is equal for all I, m must be multiple of a L I for all I, hence m is a common multiple of a L1, L2, Lk. Therefore, m should be greater than or equal to L. So, we can say that this L can be written in the form of a LCM of L1, L2, Lk is the smallest positive integer such that pi to the power L is equal to 1, meaning that L is the order of pi, and if it's order of the pi, we can just say that this complete the proof of the. So, we have a disjoint cycles are there, and then we have to all the disjoint cycles is the length, then the order of a this is equal to clearly we have to write the find in the form of this. So, consider for example, we have to consider the permutation pi is equal to S9, and then given the product of a disjoint cycle, these clearly these are the disjoint cycle, and then we have to find the what is the so this is the length of pi 1 of a length is equal to 4, pi 2 is a length 3, and pi 3 is equal to length of so pi is composed in the 3 disjoint cycles. Pi 1 is this of a length L1 is equal to 4, and then pi 2 is equal to this of length L2 is equal to 3, and then we have pi 3 is equal to 8, 9, and the length is equal to 3. So, length is equal to 2. So, this now we have to find the order of pi. The order of a pi is the least common multiple of a length of its disjoint cycles, that is order of m pi is equal to LCM of a 4, 3, and 12. So, we can simply say that in this case in the order of the permutation pi is equal to 1, 3, 5, 7, 4, 6, 8, 9 is 12. Illustrated the theorem, the order of the product of a disjoint cycle is the least common multiple of their lengths S7, and then we have to S7 is written as a disjoint cycle. We have a x is equal to, you have a 1, 2, 3, 4, 5, 6, and 7. So, we have to write as a sum pi can be written as a 1, 3, 5, 6, and then we have a this is the so we have a next left is equal to 2. So, we have a 2, and then you have a 4 and 7, and then you have a all are the these are the two clearly these two are the disjoint cycles of this. We have to find of the order, that is clearly this is equal to length of this is equal to 4 and this is a length is equal to 3. So, pi is a disjoint cycle of a this is equal to 1, this is pi 1 is equal to, we have a 1 3 5 6 and then L1 is equal to 4 and we have a pi 2 is equal to, we have a 2 4 7 and then is equal to, we have a length is equal to 3. Now, we have to take a order of a pi is equal to LCM of 4 and 3, that is equal to, we have a 12. So, again the order of a this is again we have a 12 in simple form. So, if another we have to take some disjoint cycles. So, we have x is equal to, we have a 1 2 3, this we have to write is equal to 2 3 and then is equal to 1. These are the 2, this is the length is equal to 1, this is the length is equal to 2. So, we have to if we have a theta is equal to this form, we have to, and then order of a this is equal to, we have a theta, order of theta is equal to, we have a LCM of a 2 comma 1 is equal to 1 and then we can verify that this is very trivial, 1 2 3 then is going to 1 goes to 1 then 3 and 2 then we have to take a square of this 1 2 3 1 3 2 and then clearly 1 2 3 1 goes to 1 1 goes to 1 2 goes to 3 3 goes to 2 3 goes to 2 and 2 goes to 3 and this is the identity. So, clearly if we have to just check into this form, these are the two disjoint cycles and then we have to take the order of this is equal to clearly this order is equal to 2 and then if we have to verify it by the this is means theta square is also is equal to giving the identity. So, clearly order of this also is a identity. Okay, so now we have to move further, that means the reverse of a action of a cycle. We simply transfer the cycle in the opposite direction, thus we obtain the inverse of the original cycle. For example, if we have to this we have to write is a 1 2 3 2 1, then we have to write this is the cycle 1 2 3, then we have to 3 to 2, then 2 to 1. So, we write is equal to 3 to 1. So, this is simply is we write the inverse of a this we just say that I just state previously we just said that we have a 1 2 3. So, this we have to reversing the, so 1 goes to 2, 2 goes to 3, 3 goes to 1. Now, we have to previously we find this, suppose this is equal to pi, then we have to pi inverse we have to reversing the this order 1 2 1 goes to 3, then 3 2 goes to 1, then 3 goes to 2. So, this is we just so 1 3 2 1 and this is 3 1 2. So, this is clearly we just reversing the order of this. So, we just for obtaining the inverse of the original cycle, for example, if we have a cycle 1 2 3, its inverse would be 3 2 1. So, let if pi is a k cycle, then pi inverse is also is a k cycle. More precisely, if pi is equal to a1 a2 k be a cycle of a length k, then pi inverse is also is a length of a this can be written as a ak ak minus 1 and then we have to moving to the this, we have to just take a transfer the cycle in the opposite direction, we have simply just say. So, we just move to the which, for example, we have to finding some another, we have to take a any k cycle. So, we have to take a 1 3 5 7 8 in S8. This is the cycle, then what is the inverse of this is equal to 8 7 5 3 1. If this is equal to theta, then theta inverse is equal to into this form. So, now we have to move the transpositions of permutation. This is a very important topic. So we have to just starting this. A cycle of a length 2 is called as a transposition. So if we have a cyclic notation, then if we have a cycle of a length 2, then this cycle of a length 2 is called as a transposition. For if pi is a transposition, then pi inverse is equal to pi. For example, 1 2 inverse is equal to 2 1, and the 2 1 is the same as the cyclic notation we write is a 1 2. For example, if for every k cycle a1, a2, ak minus 1 can be written as a product of a transposition. So means every cyclic every cycle of permutation can be written as a product of transposition. So we have to suppose we have a a1, a2, a up to ak. This is the cycle when now we are starting the this is a1 up to ak, a1 ak minus 1, and the a1 a3 and so on a1, or we just write into this form ak ak minus 1, ak ak minus 2, and so on ak ak1. So every cycle can be written in as a product of a transportation. If we have a cyclic notation in the permutation, then we can write every permutation into the, for example, we have to take a pi is equal to 1 4 to 3. So we can write 1 3, then we have to write as a 1 5, then we have to write as a 1 2, and then 1 4. So 1 3 1 5 1 2 1 4, and these are the transposition of this. And now this can be written in the form of this. We have to write as a cyclic notation 5 3 1 4 2. So this can be 5 2 5 4 5 1 and 5 3. 5 2 5 4 5 1 5 3. In this form we have to write into this way. Now I proved this theorem. We just proved that if we have a n is greater than or equal to 2, then any permutation pi belong to Sn can be expressed as a product of transpositions. So if we have a pi in Sn, then this can be expressed as a product of transpositions. So in view of the theorem, it is sufficient to show that this theorem, if we have a product of a disjoint cycle, every permutation of a Sn is either is a cycle or a product of a disjoint cycle. So by this theorem we can just say that we just easily write in the form of a this theorem. So we just say theorem this, it is sufficient that every k cycle can be expressed as a product of a transposition. So every k cycle can be expressed as a product of a transposition. This fact is immediately from the following equation. If E is equal to 1, then this can be written as a 1 composition 1 2. So this means if we have a 1 goes to 2 or 1 goes to 2, then we have to 1 2 1 2 1, then you have a 1 2 2 1, then you have 1 goes to 2 2 goes to 1, then 2 goes to 1 1 goes to 2. So this is clearly identity. So 1 2 composition 1 2 is equal to identity. So this is not a problem. So this means identity can be written as a product of a transpositions. And also if for k is greater than equal to 2, then I1 I2 IR, then can be written I1 IR and composition of a I1 IR minus 1 and so on up to I1 I2, where this I1 I2 IR is a subset of X, and X is you have a 1 to n. So now we have to this is equal to 1 to n. So this means we can just say that every permutation this complete the proof of this theorem. We just say that every n is greater than equal to 2, any permutation of a pi Sn can be expressed as a product of a transposition. Proof is very trivial. By using this we use the product of a disjoint cycles. We can just say that any permutation can be either written as a cycle or product of a disjoint cycle. So, this we have to prove that this means this result, and now I think this is, you can just take a for any example, if you take any permutation of a pi can be expressed as a product of a transposition. So, we have to write a this pi is equal to, you have a 1, 2, 3, 4, 5, 6, 7 as 7, we have a 3, 1, 5, 2, we have to 4, and then we have a 7, and then we have a 6. So, we have a clearly this is a as a 1, 3 goes to 3, 3 goes to 5, 5 goes to 4, and 4 goes to 2, 2 goes to 1. Then this is zero. Now we have to just take 6 into 7, then we have a 6 and 7. So, this clearly we have to taking the S7. So, this is already is a transposition form. Now, this can be written in the form of 1, 2, 1, 4, 1, 5 and 1, 3, and then you have a 6, 7. So, this is the clearly this is a disjoint cycle. These two are the disjoint, and then we can simply these permutations can be written in the form of a transposition, or we can just start from 2, 1, and then we have a this right is equal to 2, 4, 2, 5, 2, 3. This is can be also written the 2, 4, 2, 5, 2, 3, 2, 1. That is not a not a problem in this form. Either this way or this way we can just write in all the. So, if we have to any permutation by this theorem, any permutation can be cyclic or disjoint cycle. If any permutation is a cyclic or disjoint cycle, can be expressed as a product of a transposition. So, this I just stop here for today's lecture, and so we have to discuss some cyclic notations and transpositions of a permutations. And now in the next class I will continue in this permutations. We have to important class of a permutation is even or odd permutations, and then we have to find the signatures and moving in this direction. So, I just stop today's lecture here. Thank you very much.